Hello my dear students, I hope you are doing quite well. In this presentation, I am going to discuss single-phase synchronous motors. Some of the single-phase induction motors having special rotor construction can run at synchronous speed due to their specially fabricated rotors and their inherent properties. These type of single-phase motors are known as single-phase synchronous motors. There may be of two types of single-phase synchronous motors which are being widely used in industrial as well as instrumentation applications. The first one is the reluctance motor and the second one is the hysteresis motor. In this presentation, we are going to discuss particularly about the reluctance motor. We know very well that every magnetic circuit has a tendency to align itself in the minimum reluctance position to get stable position with minimum energy. The same is the working principle of the reluctance motor. The rotor of the reluctance motor gets the minimum reluctance position and gets locked with the rotating magnetic field to rotate at synchronous speed. Now coming to the construction of reluctance motor. The stator of reluctance motor has two windings, main and auxiliary winding, displaced at an angle of 90 degree as similar to that in case of split phase single phase induction motor. The auxiliary winding is provided in series with a centrifugal switch located at the rotor to open the auxiliary winding at a predetermined speed, except in permanent capacitor type reluctance motors. The stator split phase winding creates a rotating magnetic field as in the case of single phase induction motor. The rotor is also similar to the squirrel cage type rotor of the single phase induction motor. Only difference is that some of the rotor teeth are missing, but rotor conductors are still present although they are bare and short circuited at the ends, where teeth are missing so as to construct a concentrated winding on the rotor with the projected poles. The number of rotor salient poles must be equal to the number of stator poles. As in the case of three-phase synchronous motor, the speed of the rotor must be in close vicinity of synchronous speed to pull the rotor into synchronism with the rotating magnetic field. The same condition is to be used here to synchronize the rotating salient poles of the rotor at the slip speed near to synchronous speed. So, the rotor of reluctance motor is to be made as light as possible and rotor resistance is to be kept as low as possible in order to keep its running at early synchronous speed just before the synchronization. Now coming to the working principle of reluctance motor. At the time of starting, when the stator winding of the reluctance motor is excited with the help of single phase AC supply, a rotating magnetic field is generated due to split phase winding and the motor starts as a single phase induction motor. At light loads and due to lighter construction of rotor, the rotor attains a speed very near to synchronous speed, that is very small slip, and the rotor tries to chase the position of the minimum reluctance due to non-uniform reluctance of the rotor body and air gap along the circumference of rotor. This may be achieved only by locking of the rotor elevated teeth position with the rotating magnetic field, and now onwards the rotor will rotate at synchronous speed locked with rotating magnetic field of stator. Reluctance motors have approximately 1/3 or 1/2 of the power rating of single phase induction motor of same size with cylindrical rotor structure. These motors show the cogging effect due to salient pole type rotor structure at the time of starting. So, the starting torque may vary widely depending on the position of rotor at the time of starting. This cogging effect may be minimized by screwing the rotor bars and by making number of rotor bars not exactly the integral multiple of stator poles, or rather the number of rotor bars may be selected as prime number. Now discussing the characteristics of reluctance motor, the motor starts as induction motor and pulls rotor into synchronism during its running very near to synchronous speed and run onward as a synchronous motor. The motor adjusts its torque angle according to the load as similar to that of the three-phase synchronous motor. If load becomes excessive during running or starting, the motor may fall out of step and may not be pulled into synchronism. Synchronous motors operate at poor power factor, efficiency, and torque. Moreover, they cannot run at synchronous speed while loaded very heavily, so on heavy loads, they run at subsynchronous speed as a single phase induction motor. The pull-out torque of this motor is small. These motors are generally made of ratings in the range of fractional kilowatt. When they are made of heavy ratings of few kilowatts, permanent capacitor type construction of stator winding is preferred due to its better starting and running torque. Also, sometimes these motors are designed with number of rotor poles equal to the multiple of stator poles for some additional applications. This results in constant speed running of the motor at a submultiple of actual synchronous speed of the motor and is known as subsynchronous reluctance motor. Now coming to the application of reluctance motors. These motors are generally used for constant speed applications. They are widely used for timing devices, recording instruments, signaling devices, phonographic turntables, and various other control equipments, etc. I hope this presentation was helpful to you. See you in the next one. Until then, take care.